It is my great pleasure to introduce Matthew Green, who is going to talk about cryptography as a systems problem. Now, we've been looking, in the course, we've been looking at the lower level of things, starting from libraries and going down into the kernel innards. But all of that exists to support applications, the so-called layer 7 or ring 3 as we know it. And so this is going to be a look at what is it that all of those innards are really for.
Okay, that sounds. Nope, that sounds like a decent description. So I was not even completely aware that this was an OS class. So I'm gonna confess to you guys that this is probably gonna have the most tenuous connection to OS of any lecture that you're gonna hear in this course. But it might be interesting anyway, and it might be helpful at least in terms of OS. So before I get started in terms of the actual presentation, let me introduce myself. My name is Matt Green. I teach at Johns Hopkins. I'm a research professor there. I also sometimes hang out at University of Maryland. My job's a little hard to describe because a few years ago, what I did is I started a consulting firm called Independent Security Evaluators, and I spent the next few years kind of both being a grad student and also working in a consulting firm looking at real cryptographic systems. So I got to see a lot of kind of really scary stuff, and good stuff too, but mostly scary stuff, which was neat because I was actually looking at the real world. Now I'm a research professor. I do research most of the time. I still do some of that work. I asked whether I should come up here and give you guys a talk about research or give you a talk about real stuff. And real stuff won out. So we're going to talk today about kind of the systems aspects of crypto. And in particular, the example I'm going to give you guys is the SSL TLS protocol, which I think is probably the most common, widely used cryptographic protocol out there. It's what everybody thinks of when they think of secure communications. And that's it. So the last thing I'm going to add is that, as I was telling some people here, I was actually born in Hanover. So this is kind of like a kind of cool thing for me. I spent a lot of my junior high sneaking into the computer building here at Dartmouth, thinking that if I just looked really serious, nobody would recognize that I wasn't a college student. And so I would sneak in. I would use like the Tektronix terminals and stuff. It was a sad time. And get kicked out. So it's kind of neat for me to actually be in a Dartmouth College computer building and not feel like I need to look over my shoulder for somebody to throw me. So anyway. So let me start by motivating this presentation. Why are we giving this presentation? Before I even get started, how many of you guys have taken a crypto class? Okay, good. That's a good number. That's kind of what I was expecting. If you are not somebody who is really an expert in crypto, probably you've seen quotes like this around. Probably your exposure to crypto, maybe it's more than this, but at least you've probably been exposed to some statements along this line, which is that for people who know something about computer security and system design, crypto is kind of a problem that we know how to solve. Software, total disaster. Secure, everything else, total mess. But cryptography, that's the one area that really shines because we know how to do that right. Sometimes people put it like this: crypto is the strongest link in the chain, but everything else is terrible. Let's see. This is, I don't know who said this. I was trying to find Bruce Schneier saying something bad, but I couldn't get him saying something stupid. So instead what I found was this, where people concentrate too much on the cryptography of the system, which is the equivalent of strengthening. I hate this strongest link in the chain crap. Lots of people say this. So the basic point of this is, yes, if you're not a cryptographer, this might be your view of cryptography. But everything that these people are saying is wrong because crypto is just as broken as everything else. The difference is that most people don't know enough cryptography to realize that. So this presentation is going to be kind of our introduction to all the bad things that you should know about that you use in your day-to-day existence. So when it comes to those kind of solved problems, this is really what things look like. We do have one solved problem. Cryptographic algorithms, for the most part, for the minute, right now, these are actually, I would say that this is a problem that we don't absolutely need to be focusing our time on. But that's it. Everything else, and this is kind of, this arrow indicates the confidence that we have in these arrows, in these areas, but kind of in the inverse, so it gets worse as we go down. Protocol design, not so great. But then going beyond protocol design, implementation, terrible. We are just bad at implementing things. Library API design, you'd think that would be simple, right? It's encryption, decrypt, encrypt, right? not very good at this stuff. Now, I'm not even going to say anything about this because clearly we don't know how to use this stuff right, or else we wouldn't be hearing all these stories. And the problem is that probably 80% of the people on the internet don't even use crypto, which is just a whole problem that's outside of this presentation altogether. When I was looking at these slides this morning, I felt like maybe this did not give a proper view of how bad things were, so I chose to illustrate it a little bit with these guys. But that's kind of the situation. Now, just as a further illustration of kind of how bad things are right now, looks like I didn't get all of the headlines in here, but just a couple of the headlines that managed to copy over here. Lots and lots of stuff doesn't work. Oh, here we go. Sorry, this is the slide I wanted. Lots and lots of attacks that have happened over the last few years, many of them implementation-related attacks, some of them protocol-related attacks. And unfortunately, this doesn't seem to be kind of an anomaly. The pace of these things is picking up, and it's becoming more serious as more people actually start to rely on crypto. Anybody read about the Flame attack of last summer? This is, we'll come back to that, but this is, it was a very, very serious attack on certificate authority. Okay, we are not going to talk about all crypto today. That's just too broad a topic. We're going to talk about one specific protocol, which is the Secure Socket Layer, aka Transport Layer Security Protocol Suite. We care about TLS because I don't think it's really wrong to say that TLS is the most important security protocol in the world. There's things like IPsec out there. There's other kinds of crypto, but TLS is how most, at least transport security gets done these days. Most people look at this and they kind of see a vision of how TLS works that's exactly like this diagram. What you do is you're an application, you want to talk to someone, you say, okay, I would normally just make a socket connection to this person, but that's insecure, so I'll just throw TLS on it, and now it's a secure socket connection, so it's like a tunnel, and no matter what happens out here in this cloud, I'm safe. And this is not exactly what TLS really looks like, but this is how people want to view it. The other thing I should mention about TLS is not only is it widely used, but it's becoming much more widely used. You've probably seen things like this. Facebook is moving to 100% TLS. Google, Gmail has already moved to 100% SSL. Lots of people are pushing to get everybody to do this. Yes?
Is there a reason why they didn't go there before?
It's hard. It turns out to be very hard to get these things deployed. It takes more server hardware to do the decryption side. It turns out to be a nightmare when you have things like applications, like a distributed site where you have like some servers running applications and all this stuff. Getting SSL running on everything turns out to be a big mess.
Is there a factor by which it slows it down?
It does. It actually, the biggest problem is latency. So the SSL handshake is a 2-round communication. So normally if I want to talk to you, I do talk. You know, a TCP handshake is 1 round. SSL adds the TCP handshake plus the SSL handshake, which when you're doing it over like an intercontinental cable or something like that can add like a significant fraction of a second. So there's computation, there's resources, and there's latency. And a lot of people don't like that. But really the big problem is just dealing with all these other headaches that come up, like your 20 servers need the same key or certificates, and so it becomes a big headache. So that kind of stuff is a problem. But the bigger companies are slowly getting over this, and they seem to be kind of moving towards a universal TLS, SSL framework. The importance of this is that the people who are pushing for SSL everywhere are not nuts. They're not paranoid. We're entering an era where actually having secure encryption is no longer kind of an academic thing. Just, this is September 2011. Back in 2010, 2011, there was a big high-profile hack of a certificate authority called DigiNotar, where somebody stole certificates, or keys that is, and were able to make a certificate for Google, which they then used basically for everybody or a huge number of people in the Iranian internet or connection to the internet to do a man-in-the-middle attack against Gmail, where they were able to steal people's Gmail credentials. This kind of thing is actually becoming more common, not just certificate authority attacks, but all kinds of attacks against these systems, because people want to, now that people are finally using crypto, people are finally attacking crypto. So in this presentation, we're going to look at kind of a whole bunch of different problems with the SSL TLS protocol, starting not just with the way people code it up, but starting with design, starting with even some like the formal analysis and kind of what's lacking there, down to the implementation and down to the way that people use it. Before we get into all those details, I'm going to start with a very quick history of the protocol. So SSL was actually invented at a company that no longer exists, but you guys should know of, Netscape Inc. Way back in, I think, 1995. That's kind of a rough date. They had this proprietary server product and a proprietary browser at the time, which became Firefox. And they wanted a way to communicate securely so that people could do, $20 credit card transactions over the internet. So they came up with this thing they called Secure Sockets Layer. They never released the first version. A year later, in 1996 or thereabouts, they released the actual first public release, which was SSL v2. And that had some very serious bugs. And the only reason I've actually included this picture here is that for those of us who grew up in the 90s, it doesn't seem like that long ago. But when you look at Will Smith, you can see that things were different then. And in terms of the design of cryptographic protocols, our understanding of how to design these things was very, very different and very primitive compared to what it is today. Yes?
Was it SSL 1 or 2 that had the bug where they only seeded to the second, so there were only like 60 different seeds?
I didn't even include that in this presentation, but there was a huge Debian bug. Why didn't I include that in this presentation? When I get to the implementation part, stop me and say, what about
I remember one of the first releases of the Netscape SSL, it seeded the random number with the seconds clock of your computer.
Oh,
Only
okay.
60
No,
of them.
that one I hadn't heard about, but I believe you. That's not good. Yeah, I mean, it was bad. If the implementation, you'd think, okay, people make coding mistakes, but you can fix coding mistakes. But they put a lot of bugs into the protocol itself, and we're still fixing those today. So yeah, it was not an open protocol at that time, and then eventually it became open and got slowly better, but it's still getting better today, which is bad. Okay, so it had serious bugs, including apparently implementation bugs that I didn't even include here, which was fine. Okay, so that got fixed. We have a new release. I don't have the date here. SSL version 3 comes along and says we're going to fix all these problems with SSL v2. But it turns out that this has some slightly less serious bugs. However, and I did find something by Bruce Schneier to make fun of him of, he says, with Kelsey, he says, we conclude that while there are still a few technical vulnerabilities, technical wrinkles to iron out, on the whole, SSL version 3 is a valuable contribution towards practical communication security. So this is SSL version 3. Okay, he was wrong. TLS version 1.0 comes out. Now they changed the name of the protocol to TLS. It's confusing, but that's all there is to it. Instead of calling it SSL version 4, they decided to call it TLS version 1. Turns out that TLS version 1 had problems that people, even theory people, hadn't discovered yet. One of which is that the initialization vectors in encryption are not properly generated. I'll talk about what that means maybe later. But the upshot is that you can, using a little bit of JavaScript and some simple arithmetic, using XOR, you can actually decrypt cookies that are sent over secure connections. The attack that discovered this was by a guy named Greg Bard at University of Maryland. He published a paper on this. This had been known since maybe 2001, but in 2006 he published a paper that said, here is a problem with SSL, you guys should fix it. He was told by his advisor that he should probably work on more interesting publishable work, first of all. And then the paper was completely ignored by everybody until, and I'm looking at the date of this, until 2011 in September, when a couple of guys actually went out and found his paper and implemented it and made it better in the process. But they actually did this, and they called it the BEAST attack, which stands for Browser Exploit Against SSL TLS. They have this acronym problem, so they do this. They called it this, and they did a cool video of doing it, and it's really neat. You can actually take an SSL connection and watch it byte by byte, pull out this cookie out of this AES encrypted connection, which is very neat. So it turns out that these vulnerabilities were already baked into the spec, even in TLS 1.0. Later, the next year, the same guys came up with a new attack called CRIME, which stands for Compressed Record Information Leak Made Easy. And this paper took another paper from 2002 and actually implemented it, and obviously did a lot of cool implementation stuff to make it work. And they were able to do the same thing using TLS compression. So all of these flaws were in the spec, and nobody really thought about it.
Yeah. Whatever happened to these authors after?
They were killed. No, I don't know. No, these guys, they're still out there. They're working on a new attack. I hear, is this serious that they really have something called Terror? T-E-R-R.
There was a T in it. It might be called TIE.
Were they joking, or was that for real?
They do have an acronym problem.
Oh, God. Oh, man. We were hoping that they didn't do a rapid password exploit or something, because who knows what was going to come there.
They're definitely going to try to escalate their stupid acronyms.
They are. They're going to get longer, and they're going to get worse. So anyway, they have a new attack coming out. Who knows what it is, but it could be timing related. Anyway, so these things exist, and they're in there. Let me give you again. This is what you want to think of TLS and SSL as looking like. You know, this nice tunnel where you don't have to think about the details. You just turn it on, and it works, and everything you send is encrypted and protected. The real SSL protocol, and I'm still giving you a high-level view, but maybe a more accurate one, looks like this. It starts with some kind of negotiation where you and I say, hey, we support these ciphers. We both do compression. Let's talk about it. Let's agree on something that we can both support. Followed by a key exchange protocol where we agree on a secret key using public key crypto. Followed by the actual most important part of the protocol, which is to actually encrypt data in both directions securely. Followed by all kinds of crazy stuff that can happen when we renegotiate at the end of it. So I'm going to take a few minutes. This is going to be the crypto part of the talk. And I'm going to involve you guys. It's going to be an interactive exercise. We're going to see how that goes. So this is the part where we're going to talk about crypto. And I'm going to talk about these protocol design issues with TLS. The best description of the problems in SSL and TLS, the ones that are still kind of haunting us today, come from Eric Rescorla, who I think is one of the authors of some of the versions of SSL and TLS. He describes the problem here being that TLS uses prehistoric cryptography, meaning that 1995 era stuff. Uses a lot of bad stuff. One of the things that it does is it uses AES in something called CBC mode, which we can talk about later, using a MAC, which a MAC is a message authentication code that prevents tampering with the message. It uses it in a particular construction that we call MAC then encrypt. What I mean by that is we have this nice thing that, we have a message, which I'll call M, and we have this nice thing called a MAC. And the only thing you need to know about that is it protects the message. If anybody tries to tamper with this on the way over the wire, we'll be able to detect this at the other side by checking the MAC. If you don't need to know any crypto, think of it like a checksum, okay? But it's a cryptographically secure one. Then what happens is we take this whole mess and we encrypt it. This is called MAC then encrypt. MAC then encrypt. I'll come to why this is a problem in just a second, but this is what happens inside of the standard CBC mode of TLS. It uses a mode of RSA encryption with a padding scheme called RSA PKCS number 1 v1.5. And I want this to go away simply because I don't want to ever have to say RSA PKCS number 1 v1.5 again. But this turns out to be extremely broken to the point that you can actually completely decrypt an RSA ciphertext by sending in chosen manipulated messages to a server. You can decrypt an RSA ciphertext in anywhere from a few minutes to a few hours by doing that. So it's very bad. It uses RC4. I'm going to come back to why RC4 is bad, and we'll talk about that in a second. But a lot of the biggest reason that it uses all of this old, obsolete crypto is that the people who designed these protocols wanted them to be backwards compatible. So they made a bad version in 1995, and here we are in 2013, stuck with their bad versions because they wanted backwards compatibility, and they were not willing to break compatibility because they thought it would scare people away. So this is kind of the problem. All right, so let's talk about one specific example. This is a very easy one to understand. Okay, so TLS, like I just described, it MACs the record first, puts a MAC on the end, and then it encrypts it. Now the thing that I didn't show you up here is that the encryption that we use, which is called CBC mode encryption for AES, for example, has a requirement. We can only encrypt messages that are a multiple of, if we're using AES, 16 bytes. So if I encrypt a message where this whole thing comes to a total of 23 bytes, what am I going to do?
Pad it.
Good. Simple answer. That was the warm-up question. That was not a tough one. Okay, so we're going to pad it. We're going to stick on some bytes at the end until we get it up to 32 bytes. Now we have a good message, and now we can encrypt it. And obviously, when we decrypt the message, what are we going to have to do? So first, we'll strip off this encryption, and then we'll remove the pad, which means we need a padding format that we can recognize so that we can always, unambiguously take it off. That's fine. Let me actually draw in what the padding format looks like here, just for fun. The padding that they decided on TLS looks like this. It ends with a length byte. So let's see, 23 and 32, so that's a 9-byte pad. So we would start by putting an 09 byte. I always get this wrong because they do something a little weird. Actually, you know what they would do? They have a length byte that doesn't include itself. So they would put an 08 at the end, and then they would put 8 bytes. You're going to hate me for doing this. I'm just putting the bars so you can see where the separations of the bytes are here. Okay, just pretend that there's 8 bytes there because I'm too lazy to draw them all. And this would be, in total, a 9-byte pad, and that would get you up to 32 bytes. Okay, so that's the problem. So the problem here now with padding oracles, somebody very clever back in 2002, a guy named Serge Vaudinay, discovered that you can actually use the structure of the padding to do something very useful. So what happens when people decrypt is they take off the encryption. The first thing that they always do is they look at the padding. And in this case, this padding happens to have a very specific format, which is the person doing the decryption first looks at the length, and then he should expect to see 8 bytes before it. And because of the way the padding is put together, all 8 of these bytes should have the value 8. So he checks for that, simple check. And if that works, he strips it off and he goes on with the rest of it. And then he checks the MAC and whatever. If the padding doesn't check out, if any of these bytes is not 8, he usually returns an error. And the typical error is something like bad padding. Now, what could you do with that in order to take advantage of this? Well, it turns out that the CBC mode encryption that we use here is malleable. And what that means is even if I only see the ciphertext, it turns out that I can flip bits in the ciphertext that will cause exactly the same changes to appear in the underlying plaintext after it's decrypted. And so what this guy, Vaudinay, discovered is, let's give you a very specific example here. Let's imagine that the last byte, I'm going to draw a line here just to illustrate. Let's imagine that the last byte of the message that we want to attack, or the last byte of the MAC really, is an 09 byte. Okay, so what could happen here is if I send this message, I could, tampering with the message, I could flip this to an 09. Well, this message, is this going to pass the padding check? No. Okay. Well, let's say that I go and I change all of these values to 09s using the same tampering. I can just flip a bit in each of these byte positions to cause all of these to read as 09s. Now what's going to happen? It's going to say yes, there's 9 bytes of padding here, including this last byte. So I can go through every possible transformation. I can say, okay, it started at 08. I'll flip these maybe, and I'll turn them into 9s. I'll turn them into 10s. I'll turn them into 11s, and so on. So this is just a very simple example. One of those values, if I'm careful in flipping if I'm careful in changing this padding around correctly, one of these padding values will turn out to match up correctly with the last byte of the secret encrypted message that I actually want to find out. So for all the wrong things, I'll get a padding error. But for the one that actually matches this byte that I want to learn about, I'll get something else. I'll get probably a MAC error or something. And just using that condition, I've learned 1 byte of encrypted information. Now, how do I take that one step further?
You flip that one too. You go to the next sentence and flip that.
Exactly. So it turns out that I can just basically say, okay, well, let's turn all these. Let's try incrementing all these. Let's try turning these all into 10s. And okay, if the last byte here is 10, then I've learned something. Or I could try other bytes. So actually what I can do is I can flip this byte too, and I can flip it until, if this XORed with a certain value is 10, then I'll get a correct check. And if I know the value that I XORed it with, which I do, then I can figure out what the original value is here. So this is the world's quickest explanation of a kind of a complicated attack, but it's not that complicated of an attack. You could work this out. I mean, this is not something you need to be a PhD in crypto to understand. This is a very simple attack, and it's a fast attack because it requires 256 decryption attempts per byte, which is not that bad. I mean, that's actually pretty reasonable. It's like Hollywood-style decryption. You can actually really decrypt something.
And you flip it using XOR?
Yes. In fact, that's the key here. I'm not going to go into the details of CBC because I don't think that's going to add very much here, but that's exactly right. You can XOR a bit into a certain position of the ciphertext, and that same exact bit will be changed, flipped, in the decryption, except it will be 1 block further on in the decryption of the plain text. If you look up CBC mode on Wikipedia, you'll see why that is. Yes?
Is this only an attack against implementation? Because there can only be 15 lengths of padding.
This is true, but it turns out that So for example, let's say we have a case here. Let's say this is not in that 15. Let's say this is, let me think of a good one. Let's say this is FF, right? That's definitely not a valid padding byte, okay? But let's say that I've guessed that, these are all 09, and that would include this. So I can flip these all so they say 09. And then I can XOR in a value into here. By XORing this with something, let's say I'll XOR this with some value y, it will come out to be equal to 09, which will give me valid padding. So maybe that's not the best explanation. So FF XORed with some y equals OX10. And we pick y, we can try every value of y until we get one value of y that causes this thing to be equal to 10. And once we know, we know that the output here is 10, we picked a particular value, then we can recover whatever value we'll know that the input was f. Okay. So basically, this is a very bad explanation, but yes, it doesn't matter that it's just 15 values of padding. This attack pretty much works against anything, and it's a very nice attack against TLS. So to fix this attack, there's a recommended way, and there's the way that TLS did it. The recommended way is simple. It's called change the order of the way you do your MAC. You do something called encrypt, then MAC. All that means is encrypt your data first with your padding, and then stick your MAC over here on the outside. That prevents anybody from doing this crazy XOR stuff because the MAC is like a checksum and it would prevent that catch you. You'd be fine. They didn't do that. So they actually implemented a bunch of countermeasures, not all at the same time. Okay, so countermeasure number 1. This is the, if you assign a, well, I don't want to say anything rude about undergraduates, so I'm not going to. This is the, if you assign a first semester freshman computer science student to fix this problem without changing too much code, and they're lazy. Well, the first thing they're going to say is they're going to say, well, this padding error is the problem, not the encryption. Let's just make it so that no matter what happens here, we give one error. Does that fix the problem? Does it fix the problem?
Obfuscates a little bit.
Okay. Anyone have any idea what might cause a problem here?
Timing attack.
Very good. Yeah, exactly. So what somebody realized is that, so this actually, in theory, this would work except for the fact that there's a timing attack. What happens in most implementations, the first thing you do is you check the padding. If the padding's bogus, you bail. If it's not bad, then you go on and you check this MAC. That actually takes a bit of computation. So somebody actually timing you can typically tell that you've done this extra work, and then they know whether the padding succeeded or failed, and then they just implement the attack the same way they did it before. And it actually works really well because these MACs are pretty fast, but they're also crypto, so they take a bit of computation. So this actually turned out to bring this attack back to life. Okay, we need another patch. Okay, so here's another patch. All right, constant time decryption. What we're going to do is we're going to make sure that even if the padding check fails, we're going to still compute a MAC. That should fix the problem, right? Anyone tell me why that might still be a little tricky?
Power?
No, it didn't. It's not even that. I'll give you a hint. It's still timing. Still a timing problem. This is in the spec, by the way. Turns out that when the padding is bad, you don't know how long the message that you're supposed to MAC is.
Wait.
So if the padding is bad, right, you can have padding. The padding can be up to 255 bytes long, by the way. I should mention that. So if you have a valid 255 byte padding, you might have like a 1 byte message followed by a MAC, followed by a huge amount of padding. Or if somebody totally screws up your padding, you don't know if that's a 254 byte message followed by a little bit of padding. You just don't know because the padding's broken. So the countermeasure in the spec says, yeah, we know that's a problem. So what you should do is compute a MAC on something. Maybe just MAC the whole message without, including whatever might be here in the padding. Just MAC it all. Because probably that's a small enough timing channel, no one's going to be able to break it. Turns out that people can break it. Okay, and then that led to this. This is my favorite headline of recent weeks, just because it includes the word boffinry in it. I really like that. This is an attack, and I want you guys, if you can see it from back there, to look at the date at the bottom of this attack. It's February 4th, 2013. This is a brand new TLS attack called Lucky 13. Just came out this week. And the attack takes advantage of this. It turns out that the people designing TLS thought that nobody could possibly pick up that tiny timing channel. But by doing many, many measurements, millions of measurements, you can detect that. And that brings these padding oracle attacks back to life. And this is the current version of the spec. So the patch there is to write even more complicated code in your decryption library to fix that.
At least at the moment, over the internet, the latency and jitter is too much.
For the moment.
Yes.
For the
I
moment.
wouldn't count on that on the 10-year plan.
I wouldn't count on that for the 6-week plan. Especially not with the terror attack coming out as well. I mean, but seriously, I wouldn't count on that because I think that there are ways probably to amplify that. And you know, this idea that you have to be far away from things, that's kind of an old-fashioned view, right? Because in the old-fashioned view, we put our servers way out here. What's that?
Yeah, if you're on the LAN, this is a very valid concern right
But
now.
nowadays, we're all in the
Yeah.
cloud. Our server's here, and we're 3 virtual machines over. So it's very possible that we're going to be a lot closer to the attack server than we think we are. So these kind of things may seem theoretical, but they probably aren't in the long run. Yeah.
So in general, are these just bad ways to fix crypto implementation?
Never
problems?
apply band-aids. Yeah, I mean, sometimes there's not a good way, and then you're stuck. You have to find the best bad way to pick from. This is a case where doing this really would have solved all of these problems, because here, you check the MAC, and then no matter what somebody does to the ciphertext, none of these padding oracle attacks apply. And they actually had a chance with TLS 1.1 when they broke compatibility with the older versions. They had a chance to do this. They chose not to do it, and now we're stuck with this kind of stuff today. So that's one thing. With less detail, another bug that I already mentioned is called Beast. It has to do with the fact that this thing called an initialization vector in CBC mode is not picked correctly in TLS version 1.0. I won't talk about it too much except just to remind you guys that it was known since 2002, described in, I guess, 2005, and nobody really cared about it for years. It was found or discovered in 2011. The last thing that I want to mention in this section is that the practical solution is to use a cipher that doesn't have padding. Of course, a cipher suite. The one that everybody loves today is called RC4. Does anybody here know about RC4? Anyone here used RC4?
I know it's old.
It's old. It was developed. It was developed by Ron Rivest in like 1984 or something. It's
Older than me.
it's not older than me, but I was young when it was out, and it was. I actually have a demo. I believe it or not, this is a crypto presentation with a demo. I'm going to show you something about RC4 that won't curl your hair or anything, but you know, I wrote a little program. So here's the basic idea. RC4 has biases in it. A proper stream cipher should basically what it does, it outputs a stream of bits, and then it XORs those bits with a message. And the idea there is that that XORing of random looking data with a message should protect you, should hide the message itself. But it turns out that RC4, the algorithm, has biases. Certain bytes that come out of it occur with higher probability or lower probability than a real random generator would. Probably the biggest example is the second byte of the output always goes to 0 with twice the probability it should. Now that seems like a tiny, tiny little thing. There are 256 possible bytes. So it produces 0 with probability 1 over 128 instead of probability 1 over 256. How could that possibly be useful? Well, it turns out if you have the same message encrypted with many different RC4 streams, you can use that bias to actually recover what's encrypted. I wrote a program to do this. This is only decrypting the second output byte. I encrypted the value A, 5,000 different messages. I looked at the second output byte, and this program, which is not 100% accurate, as you can see, is recovering what byte is encrypted at that position. And this is, again, crypto demos suck. But this is the best crypto demo I've ever done, and it almost always works. And that would be a problem if RC4 only had a bias at the second output byte, but that's actually not the case. RC4 has biases here. At the first, this is 0 index, so the second output byte, the 16th, the 32nd, and the 48th, and I think some other ones later on. So little tiny biases, admittedly, but biases. So RC4 is an old cipher, and these things are going to bite us eventually.
Well, they already bit us in web.
Yes, RC4 really bit us in web, which is why you should not use web. But these things are still active in TLS, and RC4 is very popular, and more people today are even moving to RC4 because they're afraid of these kind of attacks. Okay, so I spent a lot of time on this section, so I want to pick up the pace because I know you guys are, this is an OS class, and I have to say something systems related at some point, right? So, all right, I'm going to skip the compression stuff. I just want to quickly talk about analysis. Okay, so a lot of you guys are saying, here's the problem. Academic security is fine. Academic cryptography is fine. But for some reason, we've entrusted the design of real crypto in the real world to a bunch of people who don't really know what they're doing, and we're telling them to do it right, and they're not listening. That's actually not the case. So cryptographers have been trying to analyze TLS for years and trying to come up with some kind of formal method for proving that it's secure. This is one person's summary of what the TLS protocol looks like in an academic paper. Anybody who's looked at TLS ever know what's missing from this diagram? It starts out with people picking random numbers and then going right to a key exchange. There's no negotiation. There's no certificate exchange. There's no exchange of any messages at all. All the stuff that actually happens in TLS, that's been the place where it breaks. So academic analysis, right now, we're still looking at like cartoon versions of TLS, and we're still not making that much progress in trying to prove them secure. To give you an example, this negotiation phase where I say I support AES and you support DES and I support RSA and you support Diffie-Hellman, the way it works now is both parties say, here are the cipher suites that I support, and then once we agree on them, once we agree on the algorithm, then we do a key agreement using the algorithm we just decided to negotiate on. Does anybody see any potential weaknesses or problems with this kind of design?
If someone pretends they only know the worst possible.
Exactly. Or if somebody in the middle does exactly what you described, edits out the messages where I say I support great crypto system and great crypto system, and leaves only the one where I support gimpy, terrible crypto system, then we end up agreeing on gimpy, terrible crypto system. This is a real problem in some versions of SSL.
Wasn't there a null cipher available in some
There's a
way?
null cipher. There were export weakened ciphers that only supported 40-bit crypto because we were afraid of exporting it to the rest of the world. Just bad stuff. Bad stuff.
Oh my gosh, that's.
But we fixed a lot of this stuff. We fixed it in sort of kludgy, band-aidy ways that nobody has really formally analyzed. They probably work, but nobody's ever actually looked at a crypto conference and said, can we prove this particular pattern to be secure? You'd think that we've analyzed this, right? We have all these crypto conferences. We have hundreds of publications every year on non-malleable, zero-knowledge, optimal round proofs. But there's only one recent publication I know of at the big crypto conference that analyzed TLS with the Diffie-Hellman ephemeral protocol. Nobody has ever done a formal analysis of the RSA handshake, which is the one everybody actually uses. Okay, I'm running out of time, so I'm going to move quickly, because this is the fun part. So everything up until now was the good stuff. This was the stuff that we know how to do well. Now we're going to talk about code. All right. We have these specs, but obviously you can't use a spec any more than you could eat a recipe. So when you implement TLS, you end up typically, you do it yourself if you hate yourself, or you use a library. Examples here, the biggest, most common one are OpenSSL, GNU TLS, which nobody really uses, and NSS, which I think is used in Chrome and in Firefox, but on a few servers, but not so many.
Pigeon uses the one you said no one uses.
What's that?
Pigeon, the chat
Oh,
program.
okay, so-
it uses it. I know because I was digging through. I'm like, this is.
They should stop. Yeah, they should stop using it. Because nobody at GNU TLS is, they don't respond to bug patches and stuff. They're
And it's like, why do you use this? It's like, well, that's what our intern implemented. I'm like,
Yeah, okay, so that deserves its own slide. That our intern implemented it in 1995. That is definitely a problem. I'm mostly going to look at OpenSSL today because OpenSSL is the most popular implementation, but it's, there are other bad ones too. How many people have ever looked at the OpenSSL code?
I've got a couple lines in it.
I can tell that it's only a couple lines because you don't have that wide, staring-eyed look that people who have really looked at the OpenSSL code look. Let me give you a fragment. Okay, this is a good piece of OpenSSL code. I just want to point you to a couple of nice features. Okay, so I like to put curly braces on some of my ifs just because I think it's less confusing, but whatever, maybe I'm picky. I have never yet put an if 0 around any code. This is a code pattern that I have never seen, but they use throughout OpenSSL to keep you, I guess, from hitting error conditions. It's a disaster. You look like you're about to say, I use that all the time.
No, it reminds me of this program called CFOG.
Uh-huh.
It was C obfuscated in the 90s.
It's very possible. There is talk of cleaning up OpenSSL to the point where we can run an auto indent program on it, but nobody can get it to that point. Because if you notice, the indenting is also crazy. This example, but actually I'm going to break out and I'm going to show you, because that example doesn't do it justice. So let's get Xcode up here, because I brought up my favorite piece. Okay, so this is a function, a very important function in the SSL handshake. Oh, well, if I zoom it, well, you won't get the complete effect of awfulness, but let's see if we can. Oh God, unfortunately, I'm not even sure how you change font sizes in Xcode. I probably have to go to preferences and. There we go, fonts, oh my God.
Try Command plus first.
I tried, it beeped at me. Oh man, well, I'm sorry. I just,
Maybe full screen it.
yeah, maybe I can, here. Oh, maybe I'll make it bigger. This is gonna end up being horrible. Come on, why can't I make it bigger? Why can't, oh. Can I just do select all? Oh, man. Yes, okay, now what do I do? Here we go. Font, here we go. Let's get you up to 18 point. And close. All right. Okay. Okay, so let's start. Here is the top of the function. SSL3 connect. I'm just going to scroll quickly. And you guys get to shout when you see the end. Oh, look, if open is blah, blah, blah. And if you see any if zeros, let me know. Okay. We're still not at the end of the function, but we are going to get there soon. Oh, no, we're not. Okay, we're still not there. Come on. Okay, this is actually getting tiring here. Go a little faster. There, oh, there we go, right there. That's the end. Not even intended all the way down to the end, but that's OpenSSL, and that's still good code. There's worse in OpenSSL. And it's very hard to tell what code is even being used and what code is buggy because it's just a mess.
Printed on fanfold paper. No function should be longer than your tool.
Yeah. Some functions in here are longer than like everybody in this room lying down on the floor would be together. There's some bad stuff. There's also some really funny comments in there. This is my favorite. If you can't read it from back there, blah, 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 blah. We should change this. This would obviate the ugly and illegal kludge in crypto mem leak CB. Otherwise, the code police will come and get us. I like that. Some of the variable names, sometimes they don't even bother with the comments. They just are just straight up clear what their variables are. But these are all minor things. There are a couple of actual serious problems here. So let's talk about a real serious problem. A real implementation of it. What's that?
Who wrote those things?
Oh, nobody knows. Nobody will admit to being an OpenSSL developer. It's like a weird secret club. I know 2 people who would now work on it, but the rest of them, they don't like talk in public. They don't like, it's weird. It's weird. And it's actually worse for NSS. I don't even know who does NSS. Okay, so this is the spec for TLS 1.2. That's the most recent version of TLS. This is RSA decryption, by the way. This is a very important part of the RSA handshake. Step 1, generate a string of 46 random bytes. Simple enough. Step 2, decrypt, this is the RSA message, to recover the plain text M. Simple enough. Now, this uses a padding scheme called PKCS1 v15 padding. If the padding is not correct or if something else goes wrong, what you do is you use this random string R that you generated in the first step instead of the message you would have gotten out. This prevents a particular attack that is very similar to this padding oracle attack that we described up here but works on RSA encryption. This is an attack that can, given a few hours, let somebody, if they're able to find out if the message decrypts with bad padding, they can actually decrypt any RSA plaintext. So this is a very serious attack. Their countermeasure is to first generate a string of random bytes, and then if there's a problem with the padding, just use those random bytes silently instead of the ones that you would ordinarily get and not produce an error. So it's very similar to what we were talking about here, where instead of producing a padding error, we kind of just go ahead with the protocol. Simple enough. How might you attack a protocol like this if you are an attacker? It's not giving you an error, but you want to find out if something went wrong. Well, you might hope that what these people are doing is not generating the random string first, but rather waiting until they get a padding error and then generating the random string. Because that might take a little extra time, and that might lead to a timing attack. Nobody would be stupid enough to do that, would they? Would they? Okay, good. So here we go. This is OpenSSL version 1.01c. This was the current version up until a few weeks ago. It's still the current code, as far as I know. Step 1 is decrypt. Step 2, if decryption fails, generate a bunch of random bytes, and then finally do stuff. I had a grad student run some experiments with that last week, and he was able to get, not big timings, but 20 microsecond timings, which are big enough that with multiple samples you can detect them over a network. you can actually probably implement a real attack on real deployed OpenSSL today using this vulnerability. It's certainly any kind of embedded device that uses this code is really in danger. And I've notified people of this, but they don't care. And they're not going to care until somebody codes up an exploit and actually does it.
You
at
need a
which
cool
point they'll care.
acronym.
I know. What do you think? Let's have a brainstorm session about that after the presentation. It has to be something better than terror. So these are real bugs that exist.
Eagle, the American.
Errors in anyway.
Yeah, given that these guys have been releasing those things in Argentina,
Yeah, I know. I don't know why they do
Giuliano
that.
Rizzo.
Yeah.
Echo Party, which I can't seem to be able to make.
Yeah, is that a real conference or do they just make it up so they can go to Argentina?
It is in fact a real conference. 2 years ago it was absolutely fantastic.
Okay.
Last year, it was pretty darn good.
Okay, so it's they get really excited about it. They have like lasers and stuff when they present their SSL exploits.
Yeah, and they have this strange, communist symbol scheme. Arms grabbing, red arms grabbing.
I'm gonna go to this one of these days just for an excuse to get somebody to
log
fund me
fix
to
or
go to
something like
Argentina. A couple other things. I guess I didn't finish with this. Not only does it generate random bytes, but there's thread locks all around this random number generator, which means if you can get two of them to hit each other on a multi-threaded implementation, you could probably expand that. The good news is that NSS does not have a set of thread locks. They have two. So this problem is not isolated actually to OpenSSL. It's in all these libraries. This one, I'm running out of time. This is another good how not to implement code example. Hard to read, so I'll just explain quickly. When you're doing a signature comparison for certain kinds of signature, the recommendation is you put your expected value in a buffer, and then you do the RSA stuff, and then you get a value, and you compare the two buffers. You do not do the RSA thing and then parse to see if the thing's correctly formatted because it's easy to get it wrong. OpenSSL, instead of doing something that would be 2 lines, does it with 20. So this is the kind of thing you see throughout OpenSSL. Now, these problems are not limited solely. I promised that I was going to talk about APIs and ABIs a little tiny bit, so I'm going to try that here. These problems are not limited to the internals of the code, which would at least be forgivable or understandable. The APIs to OpenSSL are still difficult to use. And there was a paper that came out sometime in the last few months called The Most Dangerous Code in the World, Validating SSL Certificates in Non-Browser Software from Stanford. And what they did basically is they went through a huge pile of Android and OpenSSL using applications to look for people who are not doing SSL correctly. Basically,
All of them.
all of them. Essentially, they found like 99.7%.
This is what I see all day at my job.
Yes.
No one can do this right.
That's basically it. So a lot of people, I don't even know the
Twitter
reason.
does it right.
Twitter does it right. Okay.
That's the one exception.
You think that this would be important. So the idea is you have to use the API correctly. You have to check. You have to turn on certificate verification. You have to check all these things. But people don't do it. And just by doing static analysis, they were able to find that a lot of people weren't. The reasons are twofold. One is that people do testing, I guess, and they check to see, if you don't have an SSL certificate installed on your server, well, what are you going to do just for your testing, right? You're going to flip that off. You're going to not check the certificate, and then you're going to run your test, and then inevitably, you're going to forget to turn it back on, and you're going to ship the code without having it check the SSL cert. So that happens a lot. The other reason, though, you can completely blame on OpenSSL, because you would think that in most places, if you had an int enable flag on a API, there would be 2 values for that. One would be 1, yes. Well, actually, there would be 2 values. One would be 0, no, and then anything else would mean yes. Turns out that there are 3 values, and I'll describe. This is actually a problem with CURL curl. Curl has an option called SSL verify host. When it's 0, it does exactly what you'd expect. It doesn't verify SSL certificates. When it's 2, it verifies SSL certificates. When it's 1, it does something really weird. It checks the certificate kind of like halfway. It checks to see if it asserts any host names and then accepts the certificate no matter who gave it to you. So it checks the certificate, but it doesn't care if it's actually a certificate to the site you're visiting. So simply by passing 1, which is the expected value, you can completely misuse this library and make yourself vulnerable to man-in-the-middle attacks. So this is just stupid, and this happens all over the place. And part of the reason it happens is that using any of these pieces of software, even at the API level, is very complicated. Here's an example of doing encryption with OpenSSL. Mostly this is involved with pulling an RSA public key off a disk and using it. It looks kind of like OpenSSL code does, right? It's, you know, like crazy. It's complicated. This is hard to use and people make mistakes. This is kind of the space shuttle version of how you get things encrypted. A better way to do it would be something like the library NaCl does it, which is don't make people think about algorithms. Give them a high-level API, like this one's called CryptoBox, where you basically just pass it some strings and you say encrypt this stuff, and it does everything for you with the right algorithms. You don't have to think about it. And so this is something that hopefully we will get better at doing in the future. Yes?
Is that an issue in the real world if they want to optimize, crypto, and that's why they don't want to use libraries?
I mean, no. I mean, people want to use libraries, but what do you mean by optimize?
Or like, is it? I mean, why don't people use well implemented libraries in the first place?
People use the library that is the most popular one out there and the fastest one out there. So I guess that's what you're saying, is the one that has the best optimizations. They don't care if it's a terrible, crappy library. If it encrypts AES, 10% faster, they might go for that. That's a reason. That's definitely a reason. But the real reason is there are no good, well-supported libraries out there that do everything right. You have a choice between very well-supported with lots of people working on it and bad, and not very well-supported and not deployed very much and good. And that's something that needs to change.
Of course, for development time will kill your company.
Yes, you can't afford. Yeah, you can't afford to do things right if it hurts you and costs you money. How much time do I have? Am I over time now?
Technically, this is it, but
I
you can probably have another few minutes.
Well, how many of you guys have to run to a class? Because I hate to. All right, I'm going to take 2 more minutes. 2 more minutes. The last thing I want to talk about is so simple that it will only take a minute, and then I can say thank you. This is kind of the typical experience if you ever go to a secure website. This is just human beings. After all, even if you get all the technical things right, this is what actually happens when most people go to a secure website. You don't type HTTPS AmericanExpress.com in. You type in AmericanExpress.com. And almost always what happens is your browser goes first to the insecure AmericanExpress.com site, where it then gets redirected to the secure site. And from there on, you're great. Now, this is a big problem. Anybody who's on the wire at this point can change this redirect or can do anything they want to you in between, so you don't go to that secure website. This is starting to change with the introduction of protocols like HSTS, which are hacks that basically tell your browser, anytime you go to American Express, after the first time you go there, always go to the secure site and reject any attempt to make me not go to the secure site. So we're fixing this problem, but this in practice turns out to be more important than all of these fancy crypto attacks that I've told you about. And then here's one last really, really stupid one that I love, which is that a lot of the time, this is what a secure website should look like, right? You want to have a little something in the corner that says I'm secure, a little lock. But let me move over. Sorry, let me move over to the example that I have because I'm on the wrong page. This is a big example of what often happens on websites today, which is that people stick a lock, on the page itself and say it's a secure website. This is an actual Wachovia page, it's like a year old, where they didn't actually serve the page over HTTPS, but they did put a lock on the actual HTML of the page to make you feel better. And this kind of stuff is just,
I did check, the post is HTTPS.
But it doesn't matter. If I get the page itself, I can make it post anywhere I want. So it's just, this kind of usage problem turns out to trump all the good stuff that we're doing, but we're finally fixing it. And so that gives me 30 seconds to give you my last slide, which I think sums up this entire talk. Actually, what I'm not saying is we're all going to die. I think there's a lot of good news. We're getting better at building these systems. We're getting better at analyzing these systems. But I don't think that cryptographers really take it seriously enough. Academic cryptographers are off doing multi-party, secure, round optimal zero knowledge. They don't realize that the real world, that cryptography is not a branch of theoretical computer science. And that we, and that means all of us, including people who are not grad students but thinking about it someday, should be thinking about these problems because they actually matter. And so that's it. So thank you guys.
In the class, we are going to be looking at synchronization next, and you will have fun measuring various execution paths and implementing one of these timing attacks would make a good project, so long as you would properly instrument
Yes.
the code.
Would be really cool.
So, We should open it up for questions for people who are not rushing away.
Exactly.
Alrighty then. Oh,
Very simple question. Since OpenSSL is used so popular, why now there's some kind of government agent trying to take over the library and really shift into something more secure on top?
So you think there should be, or you?
I think it should be.
I absolutely agree with you. I think the people who write OpenSSL don't, I'm not joking now, I think they really don't want to be doing it anymore. They want people to be using another library. The problem is there just isn't a good alternative to move to right now. So what people should be doing is either take it over and really fix it, or find one of the other libraries and take it over. I agree. Big problem.
Why do you think it is that those that are vulnerable, say banks or someone large like that, why don't they fund the rewriting of it?
I have no idea. I don't think that they realize. I don't think they realize how much they rely on OpenSSL, and I think they do rely on OpenSSL a lot more than they know. I just don't think it's even on their radar that these attacks are important. So I don't know what to say to it.
To not on that, it's like, cause I work with Melissa Perico too. I talk to a lot of customers constantly over like web security type things, and for the most part, it's just the awareness of it actually mattering is still growing. Because we do have some customers that are really difficult and just don't understand that these things are even important, and they're kind of grumpy that they're even spending money on it to begin with.
Yeah, I think that's. I mean, they have the money, but they have other
Right.
places they want to spend it. So,
They
yeah.
have our money.
Yeah. But they're not shy about spending it. It's just that they want to do other things with it. So.
No, but there must be an awareness because as part of their risk mitigation
I
in
mean-
terms of marketing, they
A
will
lot of
not
our-
tell us that they're being attacked.
A lot of our customers, it's someone in the organization who has influence says, we are taking $10,000 and paying for a security audit. And then the people we have to work with are like, this is dumb, I don't see, this isn't that important. This bug you found can't be practically exploited, on and on and on and on. And like, we're just here because our manager decided we're doing this.
Yep, I get a lot of that too, and it's one of the reasons I don't like to do that kind of consulting anymore. There's people who really, yeah. First of all, there's an attitude that if you can't exploit it, it doesn't exist, which is why people have to spend all this time developing these, beasts and terrors and all this stuff just to prove that things we knew were broken in the first place need to be fixed. And then the other problem is, people feel like their managers are pushing them. At least their managers are pushing them into getting a security audit. At least at least you're looking at the good stuff. The bad stuff is the stuff that you're not seeing.